This is our lab number 3, the paramagnetic lab, and I'm Sharon Gregory. So in this lab, we were trying to find the magnetic dipole moment of our paramagnet, and we were trying to find the relationship between the magnetic field on the axis of the dipole moment and the distance away from the magnet itself. And to summarize the results, we got 7.62 for the magnetic dipole moment's magnitude, and we got, for our field formula, on the axis for magnetic field, we got e to the negative 13.394 times, that's a typo, that's supposed to say r to the negative 1.469 Teslas. To do this lab, we need to know the Beer-Sort line, how to apply it to barmagnets. So we just need to know how a barmagnet is equivalent to a ring of current spanning outwards away in the direction perpendicular to the axis, to the moment of the magnet itself. And to do this lab, we found the magnometer's location on the phone, aligned it with the ruler, and then we placed the magnet on the end of the ruler so that the moment is parallel to the ruler itself and not perpendicular to the ruler. And we rotated the whole system so that we didn't have any interference from Earth's magnetic field on the X component. All of the Earth's magnetic field's effect on a magnometer is on the Y component, so we can ignore the Y component and focus on the magnet itself's magnetic field. So this is our data. We measured the magnetic field readings in the X components, and we measured the distances the distances from the phone's magnometer to the magnet associated with each magnetic field reading. So we use the formula given in the lab, B is equal to K times R to the negative N. We took natural log of both sides, and then we compared it to the equation that we developed in the fitting of the curves from our data from 2 slides ago. So using the slope of that line, we got n is equal to negative 1.469. And K, we found K by looking at the y-intercept. And which means that ln K is equal to negative 13.394, or K is equal to e to the negative 13.394. And then to find the magnetic dipole moment itself, we found, we knew that in order to find the y-intercept, we need to set r equal to 1 so that we can set the x value to 0, because ln of 1 equals 0. So if we set r equal to 1, we can just use our general equation for a barmagnet's magnetic field on the axis of the moment, which is magnetic constant times 2 times mu over radius cubed. We set that equal to k, or e times e to the negative 13.394, and we isolated mu, and we ended up with mu is equal to 7.62 amperes times meter squared. Now for the off-axis portion, we took another ruler, and we placed it we slid the phone to where we were able to get a magnetic field of 100 microteslas, and then we placed another ruler perpendicular to the phone, perpendicular to the first ruler, and then we slid the phone across that second ruler, the same distance that the phone was away from the magnet itself on the first ruler. So we slid it about 0.3 meters away from the phone, and then we placed our ruler, and then we slid it another 0.3 meters, this time in the perpendicular direction. So we compared our magnometer readings, and then we accounted for Earth's magnetic field and subtracted that from our Y components, because we're no longer dealing with just the X component, we have to factor in Earth's magnetic field. We ended up getting a net average magnetic field of 8.8 times 10 to the negative 5 Teslas. So we also use a Gilchrist model to compare our results using the magnitude of the dipole moment from part 1, which was 7.62. And this is our code. We use the general equation for magnetic field for not just on axis, but just anywhere. And then this is the results. We got 1.49 times 10 to the negative 5 Teslas, which was about less than a fifth of our results from the experiment, which was 8.8 something times 10 to the negative 5 Teslas, which we'll get to later. To do this lab, we assumed that no other electric fields were affecting the magnometer's readings. In order to assume this, we tried to isolate all the other devices in order to, devices in the room, to minimize its interference with the phone's magnometer. And then we also assumed that in part 1, we perfectly aligned the rulers so that we wouldn't have any X component due to Earth's magnetic field itself. So reason why our results were so off was mainly because human error when actually finding the distances associated with each magnetic field reading from part 1 and part 2. And yeah, when we'd move the phone a little, when we would lift the phone up to find the distance, the phone moved a little bit, which affected the distance reading and made the distance readings inaccurate. So what if we didn't align the ruler to zero out the field? We would have to do what we did in part 2, where we calculated Earth's magnetic field in the y component and x component, and then subtract it from the readings given in the magnometer, which overall makes it more complicated. What if we stuck two magnets end to end? We would essentially have double, our magnetic field readings would double in value, because we have two magnets imposing the same magnitude of electric force in the same direction. Due to superposition, we can add up the magnitudes, or we can add up the magnetic fields, and we end up with vectors in the same direction.